Shall we get started? Can you all tell me what were the concepts we discussed yesterday? So those are online. Am I audible?
Yes, sir.
Okay. So listen. Yeah. So we saw some introduction to this chapter, right? In which we saw one of the derivations. What was it? The magnetic dipole moment of a revolving electron. So what did the value come out to be? M is equal to E into NH divided by 4 pi M. That's it, no? So E into NH divided by 4 pi M. Right? When you substitute that value, what is the output? You will get 9.24 into 10 power minus 26. When you take the value of N to be 1. Sorry, 24. Yeah, 9.27 into 10 power minus 24 ampere meter square. And what will you do there? You will put N is equal to 1. And that value is known as Bohr's magneton. Right? After that, we saw the concept of artificial and the natural in the artificial magnet. So when you talk about a natural magnet, we spoke about magnetite, right? Then we spoke about the artificial magnets, which are bar magnets, magnetic needle, horseshoe magnet, and the ball-ended magnet, right? Then we saw the basic properties of magnets. What are the basic properties? 5 properties is what we saw. What are they? Attractive property, directive property, like pole repels and the unlike poles attract. Fourth is magnets always exist as a dipole, and the fifth property is magnetic induction. Right? What will a magnet do? It will induce a magnetic field in the magnetic substances which are surrounding. Am I clear with that? So now we'll get started with the next part of this chapter. Those who have missed yesterday's class, leave some space, right? Start writing from here. Okay. Shall we get started? Right. See, there are some important definitions that we need to know in this chapter, right? For the sake of understanding about magnetic substances, right? Understanding something called as Earth's magnetism, at the same time for deriving certain things. Okay. So the important definitions which are connected with magnetism are, the first thing is you need to know what is magnetic field. So name itself is suggesting what is field. Field is a region. So it is the space around a magnet within which its influence can be experienced is what is called as magnetic field. See, for example, I have this bar magnet, right? I have another set of magnet. I am placing them here. Okay, I'm not able to see an attraction. If I try to bring them close, I'm not able to take it close. See, I'm doing nothing. It is automatically turning. It's turning and it is expecting the other pole to come. So where is the magnetic field for this? For this, there is a region surrounding this. Similarly, for this, there is a region surrounding this. So what are those regions called as? That region is what is called as magnetic field, where the influence can be experienced. Influenced by whom? Influenced by other magnetic substances. Okay. Second, the next thing that we need to know is, when you talk about magnetic field, you have non-uniform and uniform, but we will concentrate on understanding what is the uniform electric field. Sorry, uniform magnetic field. What is the uniform magnetic field? Name itself is suggesting uniform means it has same magnitude and direction, right? So a magnetic field in a region is said to be uniform. If it has same magnitude and directions at all points in that region, right? At all points in that region. So at a given place, the magnetic field of Earth can be considered to be uniform, right? Whereas the field due to a bar magnet is not uniform. So generally, when you talk about uniform field, right, you always represent it with a set of parallel rays like this. Okay. So you represent it with a set of parallel rays where the magnetic field is written with a symbol B. Am I clear with this? Right. The third point that you need to know is what is a magnetic pole. So magnetic pole, obviously, you know. So these are the regions of apparently concentrated magnetic strength. What do we mean by that? So these are the regions or place in a magnet where the strength is considered to be relatively high. Right? So these are the regions of apparently concentrated magnetic strength in a magnet where the magnetic attraction is going to be maximum. Right? And where do these poles generally lie? The poles of a magnet lie somewhat inside the magnet and they are not exactly at the geometrical ends. Okay, if you take this magnet, the bar magnet, they are not exactly at the geometrical end. This is not considered to be north and this is not considered to be south. They lie slightly inside. Okay, based on this, we are going to see another term also. So concentrate on this. I hope you could understand what are magnetic poles. Let's try to understand it again. What does that mean? These are the regions inside the magnet where the magnetic strength is considered to be relatively high. So at this point, the attraction will be slightly more. Is the point clear? Right. So what about the magnetic axis? What about the magnetic axis? What do I mean by axis? Axis is basically an imaginary line that passes through something. So since here you're going to talk about a line that is going to pass through a magnet, you call it as a magnetic pole. But when it comes to axis, right, there are two ways in which axis can be defined. There are two ways in which the axis can be defined. If I hold a bar magnet like this, I can imagine a line which is passing through the poles itself, or I can imagine a line which is perpendicular to it. This also can be called as axis. Right? Because this can be axis of rotation. If I put this magnet into rotation, I can say it is rotating about this axis. Right? But here, what are they trying to say by magnetic axis? So which line are we supposed to consider? It is that line which is passing through the poles of the magnet. So the line that is passing through the poles of a magnet is what is called as magnetic axis. Meaning, for this bar magnet, how is the magnetic axis? Like this. Are you able to visualize? Right? So this is what is given here. And one point, what did we understand? North pole and south pole do not exactly lie at the geometric ends. They lie slightly inside the magnet. Justified? Similarly, we have an imaginary line that is passing through the poles itself. That is called as the magnetic axis. Then what about the imaginary line which is perpendicular to the magnetic axis called as? It is called as magnetic equator. Okay, that is what the next point is. So I hope you could understand what is magnetic axis. Magnetic axis is an imaginary line that is passing through the poles of the magnet, right? Whereas if you think of a line that is passing through, two things are to be satisfied. One is it should pass through the center of the magnet and it should be perpendicular to the magnetic axis. So it is like this. So if I take this to be the center, if I think of an axis which is passing through the center and perpendicular to the magnetic axis, then this line is called as the magnetic equator, right? That is a magnetic equator. I repeated, the line passing through the center of the magnet and at right angles to the magnetic axis is called as the magnetic equator of the magnet. And the sixth point is magnetic length. So here we are going to define two types of length. One is called as magnetic length and the second is called as geometric length. We'll be using it in derivation, so listen to this carefully. So what do you mean by magnetic length? It is the distance between the North Pole and the South Pole. Whereas that magnet has a specific length associated in terms of geometry. If you take the distance between, the North Pole and the South Pole, this distance, then you call it as magnetic length. Whereas if you take the distance between this end and this end, you call it as geometric length. Are you able to understand this? Right? So listen to this. The distance between the two poles of a magnet is called as the magnetic length of the magnet, and it will always be slightly lesser than the geometric length. So they both are never equal. That is another important point to be noted. All these questions can come in assertion reason. That is where they can confuse you. Is the point clear? So you need to be clear with all the definitions. There'll be two magnetic. Why? You can take it in any way, but mostly you will take it along the. Yeah, you can define it in that way also. You're taking it along this direction, but it will be either of them. You cannot consider both to be magnetic equators. You have to fix it as the magnetic equator for that verb. Okay, I hope I'm clear. Can you all just make a note of this? Done? Sorry, shall I proceed by the way? Shall I? Okay. So listen. The next topic that we'll be seeing is yeah. So next topic that we will focus upon is Coulomb's law of magnetic force. Okay. So before we understand what is this Coulomb's law, right? First thing is we need to understand a term called as pole strength. So by now we know what is a pole. You know what is strength. So just put the words together, you will understand what it is. Right? So each pole, like you take a particular magnet, right? Depending on the size of that, each pole is going to have a specific amount of strength with which it can attract other particles. So that's what is called as pole strength. But let's look at the technical definition of it. The pole strength of a magnet represents the inherent strength. What is inherent is? It is a natural. So natural strength of one of its magnetic poles in exerting magnetic force. So what are we trying to say? If you take a magnet, there are two poles. So you take either of the poles. For each pole, you are able to define the strength with which it can attract the magnetic substances, defines the pole strength of that particular magnet. Am I clear with that? Are you able to visualize what I'm trying to say? You want me to repeat it? Is everyone clear? So the pole strength of a magnet represents the inherent strength of one of its magnetic poles in exerting magnetic force, the extent to which it can exert force. And the question is, it is measured in terms of ampere meter. It is measured in terms of ampere meter and quantifies the pole's ability to attract or repel other magnetic materials. So this parameter will tell us the extent to which it can attract or repel other magnetic substances. So if it is able to attract faster or repel faster, it is going to have a comparatively more strength compared to the one which is not able to do that. So that's the meaning, right? And pole strength is represented by the symbol QM. Am I clear? Now, why I introduced pole strength before Coulomb's law is, like how if you recollect the Coulomb's law for electrostatics, what does it state? It is applicable only for point charges. What does it state? It states that if two point charges are separated by distance are in a region, okay, then the force of attraction or repulsion between them is given as K Q1 Q2 divided by R square. First, we say that it is directly proportional to the product of their magnitudes of the charges. Product of the magnitude of the charges inversely proportional to the square of the distance of separation between them. Same logic is applicable. The only difference is there we speak about charges because charges decide the extent to which the magnitude of charge decide the extent to which it can attract or repel other charges. Here, who is deciding? Here, who is deciding the extent to which it can attract or repel other magnetic substances? It's pole strength. Meaning, there you had charges. Those charges in electrostatics should be replaced with pole strength in magnetism. Okay. So having said that, look at it. So this law states that the force of attraction or repulsion between two magnetic poles is directly proportional to the product of their pole strengths and inversely proportional to the square of the distance between them. Almost the same, except the fact that charges are replaced with the pole strengths, right? If QM and QM are the pole strengths of two magnetic poles which are distance r apart, right? Then the force between them is given as for magnetic field. So it is magnetic force. So magnetic force is directly proportional to the product of QM and QM, and it is inversely proportional to the square of the distance of separation between them. So when you combine both, you will have FB is directly proportional to QM into QM divided by R square, and FB will be equal to mu naught divided by 4 pi times QM into QM, the whole divided by R square. If you observe, it is almost the same, except the fact that instead of 1 by 4 pi epsilon naught, you wrote it as mu naught by 4 pi. This we already saw in the previous chapter itself. Is that point clear? So this is going to be the mathematical expression for Coulomb's law in magnetic. So Coulomb's law of magnetic force, or you say Coulomb's law in magnetism. Okay, just make a note of it. It might change. It is not necessary that you're going to talk about interaction among the same strength of magnets. ஒரு பெரிய மேக்னெட் எடுத்து ஒரு சின்ன மேக்னெட் எடுத்துட்டு போனா போல் ஸ்ட்ரென்த் மாறும். அதுக்கு ஈக்குவலா தான் ஈக்குவலா இருக்கு. That depends on size. Done? Done? Listen. The next topic that we'll see is magnetic dipole and magnetic dipole moment. Right. So if you see, these words appear to be similar, right, or familiar, right? You know what is a magnetic dipole? Right? What is a magnetic dipole? A magnet that has north and south. That's simple. So in the previous chapter, if you see, I would have told you that a current carrying coil acts as a magnetic dipole. Using the clock rule, I would have explained it. So if the current is going to flow in the clockwise direction, then it is going to act like a south pole. If the current is flowing in the anti-clockwise direction, it will act like a north pole. So north and south pole will be present for the same magnet. So it is called as a magnetic dipole. And we also know what is magnetic dipole moment. What is it? From previous chapter, magnetic dipole moment is given as I into A, or you also call it as N into I into A. Am I right? If we have already discussed it there, why are we discussing it here? Right? To answer that question, we need to understand the fact that in the previous chapter, we were dealing with electromagnets. That is why when you spoke about magnetic dipole or magnetic dipole moment, you spoke in terms of current carrying conductor or current and area. But a permanent magnet, like a bar magnet, is also going to have is going to form a magnetic dipole, and it is also going to have a magnetic dipole moment. So we need to understand in terms of a permanent magnet also. Right? Having said that, let's try to understand. So what is a magnetic dipole? First of all, an arrangement of two equal and opposite magnetic poles separated by a small distance. Are you able to recollect something? Two equal and opposite charges separated by a very small distance is called as an electric dipole. In a similar way, an arrangement of two equal and opposite magnetic poles that are separated by a small distance is called as a magnetic dipole. Is called as a magnetic dipole. Right. The next question is, what is a magnetic dipole moment? What is a magnetic dipole moment? It is The magnetic dipole moment of a magnetic dipole is defined as, listen to this carefully. For a current carrying conductor, it is a current multiplied with the area. Whereas for a permanent magnet, it is the product of pole strength and the magnetic length. I'll just tell you. If I take this to be positive charge, this to be negative charge, if the distance of separation between them is 2a, then how is P given as? P is equal to Q into 2a. You remember this? Where Q is what? Magnitude of either of the charges into 2a is what? The distance of separation between them. In a similar way, here what is going to happen is, for magnetic dipole moment, instead of P, I'm writing it as M. So what did I say is the replacement for charge from electrostatics in magnetism? So charge dealt there, here it will be QM. What is this called as? It's called pole strength. So into 2a is there, no? Instead of 2a, I'll write it as 2L, where this 2L is going to be the distance between the North Pole and the South Pole. It is the magnetic length. So are you able to connect them? So that's why I'm telling you, if you know the electrostatics part clearly, it is a similar kind of pattern that will get repeated here. Is it clear? So the only thing that you need to know is, in electrostatics, charges, in magnetism, you deal with pole strength. Okay. So this QM into 2L is what is called as the magnetic dipole moment. Clear? Yeah. I told you at that point it's because you take all the distances from center. When you take it as A, when you break it as half, it becomes A by 2 and A by 2. Right? That is just a notation. எதுக்கு அப்படிலாம் போடலையே எல்லாமே 2A தான் எடுத்து அப்படி எதுவுமே பண்ணது எல்லாமே அப்படிதான் unless or until it is mentioned in question, you never take it as A, because all the derivations are derived only with 2A in mind. Center length எடுத்தனால you will always take it as 2A and then derive. So whatever formula comes, that formula is derived only when the distance of separation between the charges is 2A. Maharaj. சரியா? Okay, I hope it is clear. So let's come back to this point. Listen to this. So what is magnetic dipole moment? It is defined as the product of its pole strength. So when I say pole strength, you take the pole strength of either of the poles. So that is QM into 2L. What is 2L? It is the distance between the magnetic poles. So what is the distance between magnetic poles called as? Magnetic length, not the geometric length. It is a magnetic length, where QM is the pole strength and 2L is the magnetic length of the dipole, which is measured in which direction? This is more important. This is again important. When I talk about a dipole moment for electrostatics, if I talk about electric dipole moment, what is the direction of electric dipole moment? It is from the negative to positive. Okay. Similarly, when I talk about a magnetic dipole, here positive is similar to North Pole, or North Pole is similar to positive charge. Similarly, South Pole is similar to negative charge. If electric dipole moment is from negative to positive charge, what will be the direction of magnetic dipole? It will be from south to north. That is what is given here. See, where QM is the pole strength, 2L is the magnetic length of the dipole, measured in the direction of south to north pole. So what is the direction? It is the direction of the magnetic dipole moment. Okay. And it is obviously understood that the SI unit of magnetic dipole moment is still going to be ampere meter square. And the other unit that we can use for magnetic dipole moment is joule per Tesla. Okay, it is also called in terms of joule per Tesla. Am I clear with this? Right? So make a note of it. Okay. You're done with this, I'll proceed. Okay. So the next concept that we are supposed to know is magnetic field lines. Okay, what do these magnetic field lines mean? They are the imaginary curves which are drawn from one pole to another. I don't know from which pole to another. So they are imaginary line that is drawn from one pole to another, so that to that curve, if you draw a tangent at any point, that gives you the direction of magnetic field at that point. Okay. So if you take a bar magnet, right? If you take a bar magnet, maybe I'll try and see a bar magnet. I'm keeping it like that only. If you're not able to see, there's North Pole, there's South Pole. Okay. And so I've taken a compass. Okay. So North Pole, and I'm placing the compass here. Okay. So when I place the compass here, I'm just trying to understand if it is working. Actually, the North Pole is going in this direction because it's taking only. Not working. We need to take a real compass. Okay. So what we need to do is, if you take, okay, I'll just come from the beginning. Listen to this. When you take a bar magnet, North Pole and the South Pole, right? You place a compass here. A compass has a magnetic needle. Now what will happen is the magnetic needle will experience torque. So everything is similar. When you magnetic needle is a dipole. Magnet is there. Magnet has a field around it. So when you place an electric dipole in external electric field, what will happen to it? It will experience torque. In a similar way, when you place a magnetic dipole in the presence of external magnetic field, you experience torque. So due to the torque, what will happen is the needle will go and stop at a particular position in such a way. Closer to the North Pole, obviously, which pole of the compass will be coming closer? South, and North will be away, right? So you mark this point. Then what you will do is, you will take this compass and move it here. So when you move it here, you will observe that the needle has got bent slightly more towards the South Pole. Okay. So you will mark this point. Then again, you will move the compass. Then what will you observe? That the compass needle has got bent even more. Mark this point like this. Keep continuing the process. When you do this process, right? When you do this process, if you join all these dotted points, all these into marks, then you will get a curve, and that curve is what is called as magnetic field line. Is that point clear? Right? Now, the question is, when you take the magnetic field lines, right, what is going to be the direction of magnetic field at a particular point? So let me draw it separately. I have the North Pole here, South Pole here. The magnetic field line, due to this activity, is going to be like this. In a similar way, you go in a different path, maybe it looks something like this. Okay. So let me correct it. Wait, there is a small correction here. Okay. So it is going to be from north to south like this, like this, like this. Similarly, at the bottom also, it will be in this way. Right. So this is how it is going to be. But the question is, how did we know that the arrow mark should be drawn in this direction? What did I tell you here? I only told you that we are going to have into mark. So into mark is only going to give you a curve. But how did you know that the arrow mark is like this? So here actually, this arrow mark is following which pole of the compass? North. So the north pole of the compass decides the direction in which the magnetic field is there. So that is why if you see outside the magnetic field is always from north to south, and inside it is going to be from south to north. So unlike electric charges, where electric charges, electric field lines do not form a curved path, whereas magnetic field lines form a curved path. Are you able to understand this point? Right? So did you understand what is the magnetic field line? It is an imaginary curved path that is drawn from where to where? North pole to south pole outside the magnet and south pole to north pole inside the magnet. And tangent drawn to the curve at that point in the direction of arrow mark gives you the direction of magnetic field. So if you draw a tangent here, this will be the direction of magnetic field at this point. What is the meaning of it? Meaning, if you place a compass here, you're trying to say that the north pole of the compass will point in this direction. Similarly, at this point, this direction. If you place a compass here, the north pole of the compass will face in this direction. So it keeps on going like this. Did you understand this? Right? So if somebody asks you, how do you find the direction of magnetic field at a particular point? How will you do it? Draw a tangent to the curve at that particular point. Is the point clear? So just make a note of. And the north pole. எது கீழையா? உள்ள வந்து அப்படிதான் இருக்கு. அப்படி கிடையாது. உள்ள என்ன ஆகும்னா இந்த மேக்னெட்டிக் டைபோல் மொமெண்டோட டைரக்ஷன் எடுக்கும். இல்லையே அப்படி வராது. இட்ஸ் a magnetic that is how it follows. அப்பதானே அது curved path ஆக முடியும். It only then it will be a curved path. You're done? Those are online. Are you done?
Yes, sir.
Yes, sir.
Okay. Shall I proceed? Yes. So now we will get into a derivation. Okay. So what is the derivation? It is the magnetic field of a bar magnet at an axial point. Here, when you talk about the bar magnet, right, it is a small bar magnet. Okay. So how is it going to be? Let's say you have the north pole here and a south pole here. Right. Or maybe we can shift it also. Okay. Listen. So what is the axial? What do you mean by axial point? A line that is passing through the poles of the magnet. Right. So this is going to be the axial point. Sorry, this is going to be the axis. A point on this axis can be considered to be the axial point. Is that point clear? Imagine there is a test pole that is present here whose pole strength is given by Q T. For T, I'm writing it for test. Isn't it similar to like you placing a test charge here? You remember? So the same logic is what I'm using. You know that the length of this is going to be 2L, right? Here, what we will do is we'll approximate the geometric length and the magnetic length. Or you can take the magnetic length itself to be 2L. Okay, if you take it as 2L, this is broken into L and L. Makes sense? Now, from the center, I am taking this point at a distance R. So, from this pole, what is going to be the distance to the point P? It will be R minus L. And from the south pole to this point P, what is going to be the distance? It will be. Makes sense? Okay, what is our job? We need to find the magnetic field of a bar magnet at an axial point. Listen to this carefully. Electric field is given as the amount of force per unit charge. You remember this? F divided by Q naught, where Q naught is going to be the test charge. In a similar way, if you write magnetic field, so here what does this force stands for? It stands for electrostatic force divided by the test charge. So what about the magnetic force? It will be magnetic force divided by the pole strength. So all that we need to do is first define the Coulomb's law, or define the force using the Coulomb's law between these two poles and these two poles, and apply this formula so that you will get the magnetic field. Okay, now listen to this. Power cutter. Power cutter. Let me check in comments. Repair.
Sir, your voice is not audible.
Okay. Is it audible now?
Yes, sir.
Yes.
Yes. So if I take this point to be A and this point to be B, so what is the force that is existing between the points AP? It is mu naught divided by 4 pi into the pole strength here, which is QM, and here also you have pole strength of QM. So mu naught by 4 pi into QM multiplied with QT divided by how much is the distance? So R minus L the whole square, right? But what is going to be the direction of it? So since this is going to be positive, north pole will repel it. It is away from it. Right? It is in the rightward direction. Similarly, what is the force that is going to exist between the points B and B? It will be mu naught by 4 pi into Qm into the Q test charge, sorry, test pole. So it is the pole strength of it divided by R plus L the whole square. So it is in which direction? It will be in the leftward direction because this will get attracted to the south pole. Right. So what about the magnetic field that is generated due to the pole at point A? So what am I supposed to do? I need to divide this with the test charge pole strength. When I do that, the pole strength of the test charge and the pole strength of the test charge will get cancelled. So what will be left out? It will be mu naught by 4 pi into Qm divided by R minus L the whole square to the right. So what is the magnetic field due to B? It will be mu naught divided by 4 pi into Qm divided by R plus L the whole square to the left. Am I right? So what will happen to them? The net magnetic field at point P is equal to B A vector plus B vector. So what will you take out common? Mu naught into Qm divided by 4 pi into 1 by R minus L the whole square plus, sorry, not plus. I should write minus here. Why? Minus 1 by R plus L the whole square. Because rightward, if you take it as positive, left side is going to be negative. So it will be mu naught into Qm divided by 4 pi into R plus L the whole square minus R minus L the whole square. So R plus L the whole square minus R minus L the whole square, the whole divided by R square minus L square, the whole square. So is it not something similar to what we saw there? Same logic, no? So here observe R is going to be very much greater than L because it's a small bar magnet. That implies R square minus L square is approximated to R square. So R square minus L square is approximated to R square. R square the whole square will be R power 4. Right. So A plus B the whole square minus A minus B the whole square. It is 4AB. Right. So it will be mu naught into Qm divided by 4 pi multiplied with 4 times RL. So it is 4 times RL that you will get in the numerator. Right. 4 times RL, what I'll do is I'll write it as 2 into 2L into R. So can I do that? 2 into 2L into R, the whole divided by R square minus L square, the whole square is R power 4. So this R will cancel this R power 4 once and you will have R cube left out. What is Qm into 2L? Magnetic dipole moment, right? So what you will have is you will have 2 times mu naught into magnetic dipole moment is M, the whole divided by 4 pi R cube. Is the point clear? If you observe, this is something similar to what we saw in the electrostatics chapter. It will be 2 times Kp divided by 4 pi R cube. Here it is 2 times mu naught M divided by 4 pi R cube, where R is the distance measured from the center. Clear with this? Cancel it, Sidhu. Using this logic. Clear? Okay. So this will be the last topic for the day. Any questions? Is everything clear? Now, not many derivations in this chapter. Maybe there's one such. Okay. Mostly it's theory based. As I told you, we'll be completing this maximum by Monday, not tomorrow. Monday or maximum by Tuesday. Clear? Shall we wind up? Okay. Those are online, shall we?
Yes,
Okay, sir.
Yeah. Any you guys have any question?
No, sir.
No, sir.
Okay, we'll wind up.
Thank you, sir.
Thank you, sir.
Yeah. See you. Bye. Bye. சரி நீ லேட்டா தானே ஜாயின் பண்ண ஃபைன் உனக்கு இந்த ஒரு வாட்டி மட்டும் டேக் எக்ஸிபிஷன் பட் பேப்பர் வந்து அசைன்மெண்ட்டாக பண்ணேன் சரியா நான் டெஸ்ட் முடிஞ்சதும் பண்ணேன் தட் ஷுட் பி ஃபைன் பட் எனக்கு இன்ஃபார்ம் பண்ணாது